everyone. So I'm Jeffrey McGee from ExxonMobil, and on behalf of Zixu from Kansas State University, I would like to welcome you to the Mr. Shope's synthesis session. And to get the session started, we have Zixu Yang from East China University of Science and Technology. And he's here to actually talk about the critical roles of manganese promoters on the properties of iron-based pressure Shope's catalysts.
All right, thank you. And thank you, Jeff, for the introduction. And I'm Zixu Yang from the China University of Science and Technology. And today I'm going to share some recent research on the manganese promoting iron catalyst for the FTS process. So, okay. So first of all, I would like to introduce the FTS process. The olefins are very important building blocks, chemicals for the synthesis industry, and it can be used for synthesis of different polymers and alcohol oils and hydrocarbons. And traditionally, this kind of platform chemicals can be produced from the crude oil, but recently extensive research has been devoted to produce these value-added chemicals from the carbon resources other than the crude oil. Especially, this is very important, especially in the countries that is deficient in the fossil resources. So fundamentally, there are different resources like the coal, natural gas, and the biomass, and even the solid waste. And what happens in this whole process is that in the first step, this renewable carbon resources can be gasified into the carbon monoxide and hydrogen with these two platform molecules, which undergoes which can further be processed into the olefins through either indirect route with methanol as the intermediate, or the direct route through the so-called Fischer-Tropsch synthesis. As we all know, the FTO through the indirect route with the methanol as the intermediate has been already commercialized. But even though it doesn't, the research on the direct route is still a hot topic recently, because compared with the indirect route, it has simpler process, and it is more, it has higher flexibility, and but it also has some drawbacks. One of the main drawbacks is that the product selectivity of this process is very poor, because it is limited by the classical ASF this product distribution. But anyway, the production of the olefins through the FTO process, direct FTO process, is very promising. So then what happened? Then I'll give a short introduction on the chemistry that occurs behind that process. So what happens is that the carbon monoxide and hydrogen was the molecules were first absorbed on the catalyst surface, and then dissociation, and after that with the following carbon chain growth, and then followed by that is the termination of the carbon chain, either by hydrogenation or just dissolved as the olefins, our products. So the options of the active metals for this to drive the process allows the strong capability to dissociate the carbon monoxide. The commonly known active metals for such process are the iron, cobalt, and ruthenium. So, recently the iron-based active catalysts have been extensively researched because of its low cost and its high resistance for the poisoning, and also because iron is active for the water gas shield reaction, so it has more flexible to different hydrogen to carbon ratio. So, but there are also challenges since the iron catalyst undergoes very complicated phase changes during the activation, reaction, and the deactivation. So it is very difficult for us to identify the nature of the active phase, and also pose the challenges for the iron-based catalyst design. So up till now, the design of the iron-based catalyst falls into different, basically can force in 3 different parts. So the first one is to investigate the size effect, and other strategies like adding a second metal to promote the activity and selectivity, and or to employing the interaction between the metal and the support has been also utilized to enhance the catalytic performance of the iron-based catalyst. Also, the different methods like numerical computational modeling and institute operational characterization and kinetics were used to help us to gain better understanding of the nature of the catalyst. So, and regarding the biometallic iron-based catalyst, manganese is one of the most popular promoter used in the industry or academic research. So because it has enhanced alpha selectivity and has suppressed formation of methane, and it owns the better catalytic stability. So looking at this metal, it has an atomic number of 25, which is left to the iron. So it is less electronegative than iron, and has an atomic radius a little bit higher than iron. And the preparation method for the biometallic manganese promoted iron catalyst generally are the hydrothermal and co-precipitation and the sol-gel method. Apart from that, different configurations of the biometallic manganese promoting iron catalyst have been published in the literature. So as you can see here, we can use the manganese oxide as a support, and or we can configure a co-shell structure to encapsulate our manganese promoted catalyst. So in our study, we actually prepared our biometallic catalyst using a low temperature co-precipitation method. What happens is that the metal precursor had first been dissolved in the active glycol, and then undergoes the low temperature co-precipitation, and then after aging for several hours and wash and dry in the vacuum, and after that we calcine our catalyst precursor to obtain the catalyst. And so this is the after we calcine our catalyst, we actually measure the metal content in the catalyst. So in this series study, we used we changed the different manganese loading with the iron to manganese loading ranging from 10 to 1 to 4 to 1 and 2 to 1 and 1 to 1. So we can see on this table that the nominal iron to manganese ratios match very well with the actual iron to manganese ratios, which means that the low temperature cold precipitation method can actually adjust the iron to manganese ratio. So this slide shows the actual catalytic performance of the prepared manganese promoted iron catalyst. So as we going down from the first column shows the increasing of the manganese loading amount. So it should be noted that as we increase the manganese loading amount, we actually observe a mechanical plot for the conversion and the selectivity of C2 to C4 olefins. And also it is interesting to see that the methane, the methane selectivity is a little bit higher after the introduction of the manganese. But as we further increase the manganese loading, the methane selectivity drops. So from this table, we can initially screen our best catalyst, which is the iron to manganese ratio of 41, since it has the highest conversion and the highest light olefin selectivity. So using this iron to manganese 41 catalyst, we further investigated the effect of the activation environment on the catalytic performance. So this table shows the catalytic performance under different under syngas and hydrogen and the CO activation environment. So we can obviously see that the activity was highest in using syngas as our activation environment, and the highest the observed C2 to C4 olefin selectivity have reached to 60% nearly. And to elucidate the effect of the manganese for the FTO reaction, we employ different characterization techniques during the catalyst activation, catalyst reaction, and the spent catalyst. So for the calcium catalyst, we first analyze the texture's structure by using BT surface area and the XRD. And so it can be seen that as we increase the loading amount of manganese, the particle size decreases. And from the XRD experiment, you can see that the bulk iron catalyst is characterized by alpha and gamma iron oxides. But as we increase the loading amount of manganese, the grain size of the catalyst decreases, and the intensity of the iron physics decreases, and the manganese catalyst is dominated by the iron oxide too. So we can see that the manganese enhances the dispersion of the iron nanoparticles. And then we use the TEM to observe the morphology of the iron particles. So here it shows 3 different catalysts: the single iron, iron to manganese 41, and iron to manganese 21. So we can observe that the single iron catalyst has very good crystallinity degree with a particle size of 20 to 40 nanometers. And as we increase the manganese loading, and the particle size decreases. But if we further increase the manganese loading to 1 to 1, then the crystallinity degree decreases. So which means that further excess loading manganese can decrease the crystallinity of the iron nanoparticles. So the figure down below shows the elemental mapping of the catalyst, which also shows that the iron, manganese, and the oxygen are evenly distributed in the catalyst surface. So here is the image of the HRTM, and we can observe the lattice distance and lattice orientation of the prepared catalyst. So for the single iron, we observe the alpha and gamma iron oxides, which supports our findings in XRD. And for the iron manganese 41, we didn't observe the gamma distance. Instead, we observed the mixing phase of iron oxide and manganese oxides. And as we further increase the loading of the manganese to 1 to 1, the lattice distortion was observed. And actually we also observed the concentration of the manganese oxide phases. And to further investigate the reducibility of the activation, we use the hydrogen TBR. And so we can generally see that the reduction step of the iron catalyst follows the reduction of iron 3 to the magnetite and further to iron O. And as we introduce the manganese to the iron catalyst, the manganese enhances the reducibility of the iron oxides to iron 2, but suppresses the iron 2 to further reduces to the iron metal. So we also did some in situ XRD experiment to visualize the reduction behavior of the iron catalyst. And so we again observed that the manganese promoting the transition of the iron manganese oxide to the iron 2 oxide, but the further reduction of the iron 2 oxide to iron was suppressed. So, and to elucidate the effect of the manganese during the reaction, we conducted the CO and the H2 TPSI experiment. So here we can see as we increase the loading amount of the manganese, the dissociative absorption of the CO was significantly enhanced. You can see also the selectivity of the olefins are enhanced as well. So for the spent catalyst, we also did the XRD characterization and the BT and the particle size measurements. So basically, the enlargement of the grain size was observed, but as the loading amount of the manganese increases, the particle size also showing a decrease in trend. As we can see in the XRD pattern, the manganese suppressed the transition of iron carbide to iron oxide, which means that the manganese can increase the stability of the active phases. So this is the TM's pictures of the spent catalyst. We can see the particle sizes are bigger than the fresh catalyst, and we also did the surface elemental analysis showing that the deposition of the catalyst on the surface, but the catalyst which is doped with manganese have less carbon deposition than the single iron catalyst. So we also use the XPS to analyze the electronic properties of the catalyst, the spent catalyst, and the fresh catalyst. So from this result, we can see that lattice oxygen was removed after reaction here, and we can also show now the carbon XPS gives that the deposition was coke on the package surface, but the coke deposition was suppressed after loading manganese. So this is okay. And the conclusions here is the FTS activity and the light olefins selectivity versus the addition of manganese showed a volcano pattern. The highest selectivity of 60%, whereas C2 to C4 olefins was obtained using manganese promoted catalyst with a ratio of 41 activated by syngas, and manganese promoted the dissociative absorption of CO and suppressed the hydrogenation, which gave rise to the high selectivity olefins. So, and the average grain size of iron nanoparticles and the amount of iron carbide decreased as the loading of manganese increased. And finally, the manganese enhanced the reduction step of iron 3 to iron to magnetite and stabilize the iron 2, but suppress the further reduction of iron 2 to iron 0 and the formation of iron carbide. So that in the meantime, the presence of manganese inhibited the oxidation of iron carbide during the reaction and increasing the stability of the catalyst. And I would like to thank the students and the professors in the energy and environmental catalyst group in ECAS. And also, I would like to thank the organizer of the NAM meeting to invite me here to give this talk. And also, thanks for your attention and time for questions.
Unfortunately, we don't have time for questions. To be on time, we'll move on to the next.